Welcome to VM Easy Maths. Today's topic is the derivative of a function. We are going to focus on the geometrical meaning of the derivative. I have drawn a function's graph, the blue line. It could be in any way. This is a general function graph. And here we have our coordinate axis, the vertical axis y, dependent variable, horizontal axis x, the independent variable. Y is given, the y value is given by the value of the function for each value or x. Well, first of all, we are going to choose one point in x, call that x0, and see what the value for f is. This is f of x0. Next, we are gonna increase x0 by an increment of x. So in that way we have here x0 plus an increment of x. And what value do we have for that? f of x0 plus increment of x. And we are gonna find the average rate of change of this function between these 2 points. Here we go. The average rate of change of this function between points x0 and x0 plus increment of x is the slope of this line. The slope of a line is, as we know, rise over run. So the average rate of change of the function would be rise over run. Rise over run. Increment of the function divided by increment of x. Increment of the function, the difference between the value of the function in x0 and the value of the function in x0 plus increment of x, divided by that increment of x. Let's think of an example. Let's think that our function is giving us the value of the space covered by a certain, by a car, for instance, as a function of time. In this case, it's not x, we are going to use t. This is the space. The y-axis now becomes the s-axis, s for space, measured in miles, and the x-axis becomes now the t-axis, measuring the time in hours. In this case, the average rate of change, it will be the difference of space, the increase of space divided by the increase in time. This is what we call the speed. So the average rate of change in this case is the speed. But it's the average speed between this point and that point. The slope of this line here, the slope of this line, is the average speed between these 2 points. It doesn't matter that that car went at the same speed, was running at the same speed all the time. That would be only if the function were a linear function, which is not the case. As we can see, the speed has changed. It was going faster here, and it was slowing down here and going faster again. So that's the meaning of the rate of change in a concrete example. Let's change the increments by the actual subtractions. Here we have changed the increment of x by the actual subtraction. This minus this. The value of f in this point, x0 plus increment of x, minus the value of f in this point, x0. So this is the increment of f, and we have changed that by the actual subtraction between these two values. So this is the average rate of change. So the average rate of change is telling us the rate of variation of the function between this point and that point. But the function, as we can see here, does not vary everywhere in the same way. So what we are interested now is in finding the way the function varies in each point. That's what we call the instant rate of change of the function, and that is what we are going to call the derivative. What can we do to have a number, to have something telling us that information? Well, what we may think of is to make the increment of x smaller. Here, now we still have the average rate of change, but between these 2 points. So we still have the slope of this line, rise over run, but now the increment is smaller, so this point is closer to this point. But we are interested in finding the rate of variation at this very point, the instant rate of variation. What can we do now? Here we are getting closer. When our increment of x becomes smaller, then the slope of this line is still the average rate of change. Rise over run. But now we are coming closer to the instant rate of change in this point. To do that, we have to take the limit of the average rate of change. So that's what we are going to do. Take the limit when the increment of x goes to 0 of this expression, which is the average rate of change, and that's what we call the derivative of the function in x equals x0. That's the derivative of the function in x0. So now let's make increment of x infinitely small. Let's make it smaller and smaller and see what happens to this line, the line that we are finding the slope of. This line is the line we are finding the slope, rise over run. So let's make the increment of x smaller and see what happens with that line. Here increment of x is becoming smaller, but we still have the slope of this line here, rise over run. Let's make it even smaller. Let's take the limit when increment of x tends to 0. Here, when we take the limit, increment of x is infinitely small, and we have that the line connecting those 2 points, it touches the function, the graph of the function, just in one point, x0 is a tangent line, and the slope of that tangent line in point x0 f of x0, that is the geometrical meaning of the derivative. So the derivative of a function in a given point x0 is the slope of the tangent line to the graph of the function in that very point. So back to our example, the function that was giving us the space covered by a car, depending on as a function of the time, the space given in miles and the time given in hours. Back to our function now, the derivative of this function is what we call the instant speed. I'm using v for speed, velocity, the instant velocity in that moment, in moment t0. So the derivative of the space as a function of time, the derivative with respect to time, is what we call the velocity. That's a physical definition that we usually write. The derivative of space as a function of time is what we call, another function that we call velocity, speed.